Welcome back to Intermediate Algebra. Today, you're going to start with this scenario. On this scenario, what you're going to do, obviously read through what the directions are, look at that picture there, and then based on what we've already covered in class for using algebra, where I said actually say using systems of linear equations, you're going to make linear equations. You can see in here there are four variables, x1, x2, x3, and x4. And then also realizing that in any corner, you cannot have more people going in than are leaving. So whatever goes in has to equal how much is leaving. But you're going to then pause the video, spend some time, and it's taken some time in class. Typically, 25 to 30 minutes with a group of people really thinking and contemplating. So if you're struggling to get going on this, that's understandable. But take some time and start figuring out some equations related to all these numbers and the one-way direction of what's happening. That's what that means. So this means there's 20 coming in. This means there's 25 leaving. So using that information, spend some time and see if you can figure out how to solve this. We will come back and have at least a partial solution before we move on in class. All right, so where we started was looking at a corner. So if I look at that individual corner, we're looking for what's going in and what's coming out. And we said x2 is going in, 25 is coming in. So that there, we said, was x2. Got to turn my pen back on. There it is. x2 plus 25 is going into that corner over here. x2 and 25 are going in. And then whatever goes in, we have to have the same amount leaving. So what's leaving is 25 and x3. So that was going to be x3 plus 25. And those are equal. And then in the habit of doing equations, I look and see, oh, wow, they both have a 25 on each side. So if I subtract 25 from each side, whatever you do to one side, you have to do the other. I know that x2 is the same as x3. Well, that's helpful because I can use that later. If I move to the next corner, and again, where you start doesn't matter. You're all going to end up in the same kind of place. I move to this corner. I see x3 is coming in. 20 is coming in. So I have that corner will be x3 plus 20 will equal whatever's leaving that corner. And leaving that corner is 25 and x4. So x4 plus 25. I look at this and I'm going to do the same thing, but here I'm going to just pick the smaller number. I'm going to subtract 20 from both sides. So I have x3 is equal to x4 plus 5. Again, because if I subtract 20 from this side, I have 0. If I subtract 20 from this side, I'll have 5. And I know later on if I need to, if I want to swap that x3 with an x2, I can because they're equal to each other. All right, so I can do some substitution later. All right, I'm going to set up a third equation, and I'm going to work in that bottom left corner. I have x5 coming in. I have x4 coming in. That's a 4. x4 coming in, and that must equal what's leaving, which is x1 plus 20. All right, that one's got 3 variables, just the one number. There's really not anything else I can do with that one at this point. So I'm going to grab the fourth corner, and what do I have coming in there? I have an x1 going in, and I have 25 coming in. And that will equal whatever's leaving. And what's leaving is an x2 and a 30. Again, same habit. I'm looking at this. I'm going to subtract 25 from both sides so I get x1 all by itself. And that will equal, if I do this here, that's not an equal sign there, folks. That's a plus. So I subtract 25 from both sides. I have x2 plus 5. And now the other advantage I have is now I've got smaller numbers. But then I can start doing substitution to get rid of some variables. So where can I substitute some things in? Well, I can change, I can pick a variable to get rid of. If I pick to get rid of x3s, I would then have, slide that up and I'll make that smaller. Ta-da. So if I choose to get rid of x3s, I'm going to have x2 equals x4 plus 5. And that was from this equation here. All right? Do I have any x3s here? Nope. Do I have any x3s here? Nope. So what I now have is I have one equation. I'll have this other equation, x5 plus x4 equals x1 plus 20. And I have my third equation, which is x1 equals x2 plus 5, which is this equation here. I've got three equations. I've got three variables. Now it's a matter of trying to find a way, is there anything else I can substitute somewhere to get rid of something? If this has exactly two variables, which it does, and this one has the same variables, but they don't. This has an x2 and an x4. This has an x5, 4, and 1. This has a 1 and a 2. If it were just two variables, I could finish this out exactly like I started and did in the last time that we met. But now I've got three variables with three equations, and that's what brings us to today's content. All right. It's possible that you worked this out and figured this out quite quickly. I could take this here, that x1 equals this. What does this x1 equal? Well, if I subtract 20, I would have x5 plus x4 minus 20. That equals x1. Over here I have x1 equals this. So that would mean, come on. Keep sliding this up. Those two equations would have to be equal to each other. If they both equal x1, that means they equal each other. So I'd have x5 plus x4 minus 20 equals x2 plus 5. Do I know what x2 equals? This x2 right here equals this. So I could take this and substitute it in. And you're going to start getting this over, like we're going to keep repeating this process until we can get rid of a variable completely and find out what each individual value is. There are going to be other techniques that'll make it a little bit quicker, which we're going to cover today in class as we get to three variables. Actually, we ended up with more than three variables, didn't we? We have x1, 2, 3, 4, and 5. So this is quite a complicated mess to work our way through, but it's good to start thinking, where can I go? What kind of methods can I use? Am I using substitution, elimination method? And then today we're going to learn a third method called matrices. And I'll preface it already with, you don't have to use matrices. When you get to anything three variables and more, matrices are faster. All right, because it helps to keep things organized. In this case, well, you can see already, it's hard to keep things organized when you have 5 different variables going on. But anyways, so from what we covered the other day in class, that got us to this equation, which is the percents. So the total amount, the percents, and the other fun nugget of info, that the small account is 4 times the large account. Or the small account's 4 times the medium account, that is, for what we defined over here. Plugged that in. This gets to be 5y. And then over here, we plugged in the 4y. That's 0.16y. They add together. I end up with this equation. I have 2 variables. I have 2 equations. The next step would be to solve for y and z. Elimination method's the first way to go. But before we do that, I am not a fan of these decimals. So the way to get rid of those decimals is multiply by whatever's going to get rid of it the most. What do I mean by that? This is 3 decimal places, so I'm going to multiply it by a number with 3 zeros. If I do that, I have 215y plus 60z equals, we had 1,300 and then 1, 2, 3 more zeros. 1, 2, 3 more zeros. I now have that equation. I'm going to bring this one down. 5y plus z equals 24,500. I now have 2 variables, 2 equations. Elimination method, the easiest one to get rid of here, in my opinion, is the z. Why? Because this z right here is just got a 1. So I'm thinking, what would I multiply this equation by to get rid of that z? I'm going to multiply it by negative 60. And if I do, I will have negative 300y minus 60z equals, and here I don't know that number off the top of my head. Someone with their phone out is going to calculate that number for me super quick. Those of you in class, any questions on that? Yay. This is what you're going to do at the boards. You can erase yourself if you want to take a picture of that quick, and then we'll flip the screen up.
This one, JP. You probably know this stat.
You can probably look it up because it's truth. But I want you to use algebra to figure it out, not the internet.
Exactly.
All right? I'm going to shut down the projector and pull up the screen.
I'd score more in a season, if I'm being honest.
Uh-huh. All right. Ready? Okay, well, someone told me to get that later. Oop, it didn't shut off. I'll get that. There you go. Oh, yeah. Hold on. There you go. Thank you. Yep. Just a regular 2-point shot's called a field goal. I know it's confusing because in football, field goal's 3. Is I would take this equation and I'm going to put that x into this equation. And that will eliminate the x's. I'll no longer have x's. So when I do that, slide that up over there, I will have, go with yellow, y equals, and I replace the x with the other thing, 127 plus 3z minus 46. And then I'm going to simplify that by subtracting the numbers, right? Just bring them together. So 127 minus 46 is 81. So y is equal to 3z plus 81. You could have 81 plus 3z, it doesn't matter. I'm now going to take that and replace it in the other equation, but I'm also going to do the same thing over here. So this, wherever the x is, I'm going to replace it with this number. So this is going to replace that x. So that x gets replaced and becomes 127 plus 3z. Then the 2y is going to be plus 2 times this. This is going in for the y. 3z plus 81. Then this 3z comes down just as its own, plus 3z equals 2593. So it's finding a way to combine equations to eliminate all but one variable. Are there other ways you could have gone about this? Yes. This one is going to keep me away from a lot of fractions because I substitute the y in and substitute the x in. So if you're thinking about a general procedure, it's, can I take one equation, sub it into the other equation, and then take those first two original equations and sub them into the third equation? Something to get it so I only have one variable. And because I saw at the beginning, I only had an x equals over here and a y equals over there, I'm like, well, eventually those are going to, and sometimes our habit is, well, what if I take this and plug it directly in for the y? And what if I take this and plug it directly in for the x? That is okay, but then I still have two variables. So by taking this equation, plug it into that one, and then take whatever that new equation is plus the original one here, plug them both into the second one, that's going to get me so I only have z. So procedurally, it's trying to find a way to get rid of, obviously, can I plug one into the other one and I eliminate a variable? The minute I eliminated the x over here, because I plugged that in, boop, just subbed it over here, then I noticed, wait, I only have a z. And then I looked over here and I said, oh my gosh, I only have a z. So getting them both down in here, and then it's a matter of algebra. 127 plus 3z plus 6z plus 162, because 2 times 81, plus 3z equals 2593. And some of you say, well, can't I do this, and can't I do that, and can't I start combining these things? My caution is always don't combine too much too soon. On the left-hand side, I have 3 plus 6 plus 3. I have a total of 12 z's, 3, 6, and 3. And then for numbers, I have a 9, an 8, and a 2, and this equals 2593. Subtract 289 from both sides, and that's where I'm not necessarily, not necessarily showing that step because we're now beyond Algebra 1, but 2593 minus 289 is 2304. If you show the step, there's nothing wrong with that. Divide by 12, and if I've done my math right, it should be a nice, easy whole number. So in that year, which I want to say was 2013, 2014, whatever year it was, Katie shot 192 three-pointers. Take that information, put it right there, and I'm going to find out how many field goals he made. Take that information back up here, and that's going to tell you how many free throws he made. Last thing for content for today, got a couple slides on this. So now we're moving beyond the 3 variables, 3 equations, and we're going to graph and solve these super quick. So graphing and solving. So here's a matter of, yes, could you just pull up Desmos and graph this super fast? You certainly could. But because you're not going to have Desmos on tests and quizzes, X is Y. Remember how we do this? 1, 2, 3, 4. We're going to label them. That's 4 and 4. Try to make them equal, even though I didn't. -4. -4. We'll see if we can get that way far enough. They're both in slope-intercept form already. So as my quick refresher, that means this is my y-intercept for that equation. So that equation will do in yellow. The y-intercept is 1. The number in front of the x is a 1. As a fraction, 1 is 1 over 1, which means it's rise over run. So I'm going to go up 1 over 1 and make a dot. Up 1 and over 1, make a dot, etc., etc. Down 1 and over 1, down 1 and over 1. Ooh, that was, we missed. Try to hit all those points. I draw my line and then I look back at this. It's an inequality, which means I'm going to have some shading, but also inequalities I have to remember. Is it open dot or closed dot? Well, in this case with a line, I say is a solid line or a dashed line. Because it's equal, it's solid. If this were just the symbol greater than, it would be a dashed line. But then I look at this and I read it left to right. Y is greater than, because that symbol is facing the larger value is over here. So y is greater than that, which means when I shade my graph, I'm shading above the graph. Go to the next graph. My y-intercept. Now here it's written the other way, so be careful. Don't think that just because it's, and if it's helpful to you, rewrite it. Y greater than or equal to -x plus 3. That negative belongs with the x. Don't just switch the things around and have the minus stay in the same place. The negatives always connect to what they're immediately in front of. So there, my y-intercept is +3, which is right there. My slope is -1. -1 is the same as 1 over -1. Or in other words, it's down 1 over 1. So down 1 over 1, down 1 over 1, down 1 over 1. You get the idea. And if you've drawn a fairly neatly done graph, which mine is not, you're going to hit all your points going through. I look at this symbol, and that symbol is greater than or equal to. Equal to means it's a solid line. Greater than means I shade above it. And then, when you have a system of equations like this, the solution is wherever it's shaded from both lines. So I'm going to redraw with a thicker blue. There, here, and the two areas that are shaded with yellow and white becomes my zone. This up here is my solution graphically. So in a graph where I have two inequalities, I'm going to have more than one point typically as a solution. When we did graphing, when we just had single lines, we said, hey, two lines are going to intersect at a point. Or if they're the exact same line, it's going to be an infinite number of points. Or if they're parallel, there's no points. With inequalities, in this case, any point in this area. So if I pick the point 1, I don't know, pick a number up there. 7. 1, 7. If I were to take that and put it into this equation, the y is 7, greater than or equal to, the x is 1 plus 1. Is 7 greater than or equal to 2? Yes, it works in that equation. What if I take it and put it into this equation? 7 greater than or equal to 3 minus 1. Is 7 greater than or equal to 2? Yes, it works in that equation. Any point and every point in this zone is a solution. So no longer do we have a point. No longer do we have no points. We're going to have an infinite number of points, but it's not because they overlap, but because their areas overlap. With these, I'm going to show these quick because they tend to cause people some angst. So this is x, this is y. Conceptually, where is x less than or equal to 2? Well, here's my x. I better put some markings on here. 4. Ran out of room, -3. 4, pretend that goes up. -4. So I look at my graph and say, where is x less than or equal to 2? Well, here's my x. Here's 2 right there. Where else is x2? Well, right here. And how do I know that x is 2 there? Because the coordinate is 2, 1. Right here, 2, -1. Right here, 2, -2. See what's going on? I have a vertical line. And the x-coordinate on every point on that line is 2. So where is x less than or equal to 2? Everything to the left. So this whole zone out here gets shaded. Then I've got y, and it's -3. So I go on my y-axis to -3. Where else is y going to be -3? Right here. Right there. Right there. That point there is 3, -3. Every point along that line is, oh, and I'm drawing solid lines. I should really make sure. Oh, yep, because it's equal to, greater than or equal to, it's a solid line. That one's a solid line because it's less than or equal to, the equal to being solid. The yellow shades above. And then I look to the zone that they're both shaded, and I have this as a boundary line. I have this down here as a boundary line. And everything in between was double shaded. So when solving inequalities as equations of lines, the typical way of solving it is by graphing. So it says graph to solve. This would be harder to do if I just said solve it algebraically. All right. Solving by matrices, I am going to add this on my own and add it to the video that you can watch later. And like I said, if you like it, use it. If you're like, I like the other methods for solving, then stay with that. All right? If you're going to plan on doing anything in the engineering field, you're going to want to learn matrices because you're going to start doing stuff in 3 dimensions that will start looking like this equations and saying, okay, solve for x, y, and z. It's just much easier to get in the habit of doing that. Or if you decide, wow, I'm really inspired by math. You, professor, just really want me to make me want to be a mathematician. I'm going to go into that. You're going to have a whole class that does this all the time. And you're going to find out it's actually really quite useful tool. Has a lot of fun aspects to it. And then last thing, this is my reminder. This is all listed on the Canvas page. I should never have to put this at the end, but I seem to always do. You're going in there. You're working on these problems out of your book. You've got the red one, or not the red one. You got the green book that we've been using for this class. You're working on all those problems, and most of them have solutions. Like this one won't, and that one won't because they're evens, nor will this one. Because I'm never collecting this, if you look at 36, and you're like, I don't know how to do 36, look at 35 and look at 37. Because the answers to those are in the back of the book. If you are struggling and want to try more, you can always do more. And that's the sign, I'll be honest, and this is not trying to sound arrogant, that's a sign of good students. You realize, I think I get this, I don't know if I get this, I'm going to try one similar to it, solve it. If I get the right answer, because I choose an odd one, then you know that you have it. This is just a launching point, a getting starting point. And then if you're getting all these, it's not a bad idea to pick a couple near there. Try those as well. Again, we had an 1.5-hour class, which means you're spending 3 hours minimum on this. For every 1 hour of class, you spend at least 2 to 3 hours outside of class, working on it, watching the video again, rewriting your notes. This is what students who really desire to be successful do, which I'm assuming you all want, but just as a good reminder. It is now time to go.